Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering, and welcome to this week's Inside Chips podcast. I'm here today with Shai Cohen, co-founder and CEO of proteanTecs. Shai, looking back at 2025, there were a whole bunch of trends that arrived faster than anyone expected. So you think about there was an explosion in AI data centers. There was the edge build out. You got robotics and photonics is coming in. On the far horizon, we're even looking at quantum. We've got multi-die assemblies that are really taking off. What surprised you most in terms of the impact of these changes and also the speed at which they came?
You made a very broad comment about huge progress in 2025. And you're right by asking this question. I am astonished by the progress. Both of us live here for a long enough time, and everything we've done so far seems to be so linear with respect to the progress in 2025, which is completely exponential. The biggest surprise that I have is actually the pace. And you mentioned AI, data centers, robotic, the silicon photonics, which is coming into realization after so many years, including me involved in that journey of trying to make silicon photonic production worthy. And here we go. 2025 is the year. And maybe to mention some more things that are happening, there is so much of consolidation and verticalization that is going with the hyperscaler doing stuff and the solid semiconductor companies that are becoming vertical as well, and the ASIC play, which is changing on a day-to-day basis with every big company getting into the game. Very surprised by the pace of things. I think we're lucky to be able to watch it and to be part of it.
You still got some of the same issues that you're dealing with before. Power is one of the big ones. So you still got the problem of getting enough power to the individual transistors. But power also generates heat. So now you've got the current problem. How do you deal with that? What sort of impact does that have over a long term? You've got performance issues going, okay, we can only crank up the clock so far because suddenly you're going to get too much heat that is localized dependent upon the individual workload. This all has an impact down the road on how long are these chips going to last? How long are they going to be reliable? How do you know they're going to be reliable? So you've got a lot of pieces that are really tightly intertwined and in a way that they've never been in the past. So what do you do about this? What do you see as the new opportunities? What do you see as the new innovations that are needed? And what's going on long term if you look down maybe 5, 10 years?
We have our own of that, and it's true. It's true that once there is such a verticalization and consolidation, and now that the chip is just a component in a system, that the system is a component in the rack, and the rack is a component in the pod, and the pod is a component in the data center. I think today, with huge challenges related to power delivery, even at the top level, down to the rack level, down to the system level, and then to the chip level and the transistors, as you mentioned, and then keeping the performance high and keeping the overall economy right for the service provided, we as a company are lucky to be in exactly where I think one of the solution lies. And that's the fact that with all those challenges, the need for an end-to-end optimization becomes a necessity. There is no way anymore to make the best chip ever and then the best system ever and then the best rack ever and then build a data center out of all of this, because there is too much performance and too much power that are left on the table. Therefore, a technology that can help optimize the overall solution, meaning with the end result. And the end result, as you've mentioned, is the actual service running, the actual application, the actual workload running. The whole point now is to make sure that for every workload, and I would even say not just a workload as a unit, I will go one step further and say even within the workload, every couple of clocks or even every clock, we need to optimize the power and the performance such that there is nothing like no margins or no guard bands left on the table, so that the overall power consumption is the lowest, the overall performance is the highest. But the difficult part here is to keep the systems out of failure, so that if you do all of this, and at the end you have too many failures, it's nothing. It's worth nothing. So the point is to optimize from the chip through the system to the specific workload. And even inside the workload, sometimes the workload is very busy, sometimes it's not. And make sure that the optimization is such that the power delivered is the absolutely necessary power and nothing more. And performance scrutinized is the maximum that can be scrutinized at that period of time, but permitting no failures, that may be the solution. And while you do that, I want to touch, just if you don't mind, just to touch upon one more comment that you made. If at the end we're able, if the industry is able to optimize in such a way, then the voltage would be the lowest at every point in time, and the temperature will be the lowest at any point in time. And by doing that, the lifetime of the equipment will extend. And from experience, I can say that today in large implementations in data centers, let's take an example of reducing the chip power by 10%. The temperature will follow and will be reduced, say, 10 degrees, just to round up some numbers. 10% less power, 10%, 10 degrees temperature reduction. The resulted lifetime extension is about 1 year, which is almost 20% of the predicted lifetime.
Most of this, though, has been done in very controlled environments in the past. So you think about data centers, they are cooled to a certain level. The workloads add another dimension to this, of course, because now you're dealing with different levels of computing that are going on at any particular point. But this also becomes more difficult to regulate, to understand as you get out into the field too, right, with the edge. So you think about a car, for example, and that car is sitting in the sun in Phoenix, Arizona versus Fairbanks, Alaska. It's going to behave very differently there. It's going to have a different lifespan in addition to whatever you're predicting for this is supposed to be what the norm is.
That's very true, and it requires really some additional layers of let's say, management, data center management or car management. There is a huge development today with fleet management, and the fleet management can be associated with the data center or with fleet of cars. But the need now is an additional layer where things are happening real time. Because as you've mentioned, like the conditions in which the system is being operated in is a matter of course, the temperature and the stress and the workload and so on and so forth. Some of it is okay to be managed in a population analytics kind of method, where, if you have something working in an environment which is much hotter or much colder, and it's a general condition of that environment, that's one, and that can be handled in large scales. But the point is that if you want to really scrutinize each system and each device workload and work in every component and minimize the power consumption of each component and gain by aggregation a lot of power reduction at the higher levels, then the need to do the power reduction techniques are real time. And this has to work in conjunction with the actual applications or with the actual workload. It cannot be dealt in a test mode or something like that. It has to work in mission during the application and kind of work on the side and provide the insights and the telemetry up to the machine to take the decisions about power reduction or performance optimization on the fly while it's working. So if I'm going back now and describing the whole thing, in order to have a very efficient fleet management up there, having a system that can work in an individual manner on every device and configure every device to the lowest power, highest performance point based on the actual workload that is running at that point in time, then the aggregated result would be an enormous power reduction.
You no longer can fit all of this stuff into a single chip anymore. It's now being broken up into chiplets. It's being broken up into heterogeneous die. And that adds a whole element of complexity that we didn't have before. How do you deal with that? You're looking for the same issues in terms of, are things heating up too much? Are you starting to see data slowing down somewhere? But you're also looking at this from a standpoint of, this is no longer just one chip.
It's true. It's not longer one chip, and even in many cases, no longer the same provider. Each die can come from a different supplier, and the packaging party can be even another party, another business running packaging or whatever. Like I don't think there is any magic solution here, and all the current methodologies should be applied even better and even farther. All the current BKMs about testing and shifting left things and so on and so forth. And of course, the assembly becomes even much more complicated. And whom to blame when there is a problem is another aspect. And then also the cost of a failure is much higher when you stack so many dies and so many things onto a single package. The problem is really big. We will make 10x better visibility into what's going on inside. And inside, I mean in each and every die. And then in between the dies on the interfaces, if we make like 10x improvement on the visibility of what's going on inside that device, then the ability to understand what's wrong would be much easier. And this can start even at the lower level, like even before assembly, when you do the sort testing. And during sort testing, you get a higher level of visibility. You can avoid assembling the wrong die onto a multi-die package. Also, there is an opportunity if you have enough information coming, another layer of telemetry coming from each die, then the selection of dies onto could be complementary, so that now you can even optimize, let's say, performance or power or yield in terms of selecting the right dies to work one with each other. Let's say you have 6 different or 8 different dies coming onto a single multi-die package. Then if you're shooting for, let's say, a low power bin, or if you're shooting for a high performance bin, if you have enough visibility into each of the dies during the sort testing from such perspectives, then you can mix and match dies earlier in the production process.
In the past, when you put in a lot of your agents, you typically did that outside of the individual die. It was a lot of the interconnects. Does the placement of them now change because you're now dealing with multiple die and multiple different kinds of workloads?
The placement of agent is mostly related to the end target of the customer. So, for example, if the initial reason for putting such agents is to manage power performance, to make sure that we're able to operate for every workload and on a clock by clock basis inside each of the workloads, and create a minimum power and maximum performance and avoid throttling and such things, then the placement would be associated with that end result, meaning the placement should meet the need that whatever the workload is, and on each clock there will be a high or 100% correlation with the performance limiters that time. So that will determine implementation and the selection of where to put these agents. If there are other applications, for example, some of the agents are, let's say, are measuring spatial effects, for example, temperature or process-related parameters. In such cases, the placement of such agent would depend on the process that is being applied, meaning it will be implemented in a spatial way. For example, let's say that you want to measure in a high granularity a specific process node, then you will probably put a kind of a process agent every few millimeters square. To the point of multi-die packaging, some of these agents needs to sit on the edges. Yes, that may be the difference in between multi-die and regular die, where in multi-die there is a higher importance to provide visibility into the edges so that you know what's going on in between the dies as well.
So this becomes a major floor planning issue that you have to deal with right up front. Where do you put the agents, and how do you make sure that you're getting the data that you need dependent upon your workload?
So luckily, technology is going so fast, and the ability today to provide the right logic and the right instrumentation, kind of EDA tools and the right algorithms behind such placement, this is all done automatically as part of a place and route flow. So that actually from after the configuration of the placement is being determined only at the very first time of the project, where the architects of the project usually sit down and they decide their business result. They decide power, they decide the performance, they decide the reliability, lifetime, all the aspects that the agents can later on provide some insights and actionables to them. So they configure a compiler at the very initial stages of the design. And from there on, they will get the right implementation for their business needs in an automatic manner.
So, how do the agents themselves age? Are they reliable all the way throughout the lifetime of a device, or do they need to be backed up as well?
So yeah, that's questions that are being asked a lot, and it really depends on what is that you're measuring. When you're trying to measure, let's say, temperature, then the accuracy of the temperature measurements should maintain its specifications throughout the lifetime of the device, and that's something that can be simulated and guaranteed by design. So that some of the elements, when you measure voltage, when you measure temperature, this is kind of easy, because you just have to design it so that even when there is aging, then the accuracy of the measurement is still there. Some of our logic, which is probably the most useful one for power reduction and for performance increase or throttling or preventing, let's say, false positive throttling kind of things. These are gates that are part of the design itself, and they age with the design itself, and they measure the margins on millions of parts inside the chip. So by definition, it has to age with the circuits themselves. I think if in the past people were trying to gauge, let's say, the performance based on some adjacent circuitry, let's say some parallel path that are being used to kind of imitate or the actual path that are being exercised. Now the margin measured is part of the logic itself. So we're actually sitting on inside the logic itself, and therefore there is no need to take into account the aging effect. It's part of the game.
So that produces a lot of data that you're having to wrestle with. How are your customers using that data? And even beyond that, when you start getting into a heterogeneous system, who owns that data?
Many of the applications, much of it has to go real time, and or near real time means edge software. So these ones are things that are happening without even generating data going outside. All the decisions are taking place in firmware or hardware inside the chip based on the telemetry that is being collected inside the chip itself. So, and it doesn't have to be like very data dominated, because you can always decide on thresholds and work accordingly and get to the best results that you need. And these thresholds can be controlled by either the software or during characterization, what so. So much of it does not even require data to go out. Many of the applications are running real time, and there is almost no data going out. Now, in order to provide other aspects of the solution, for example, if you want to correlate tests from chip level, let's say sort or final test at the chip level, and compare it with even system level test at the chip level, or system testing and then in-field operation to compare apples to apples, meaning do the same measurement but get different results because of the different environment. So because the tester will run test, and in field the application or the workload will be completely different, but you read the same data, and now you have a ruler that can tell you, you know what, the same measurement looks different, and this is the correlation that you have in between silicon system and in field. In such cases, yeah, the data has to go out. The one owns the data is always the one who is using. The user owns the data. We never own the data. The data is owned by the customer. As you said, there is a lot of information that is being produced and being mined from the chips with our technology. The agents are being connected through a hardware monitoring system. This by itself contains some data processing. Some of the data is already being processed inside the chip by our system. then some of it goes out and being consumed by the applications. And the applications can be either firmware or even hardware, or firmware applications or edge applications or fleet management applications on all the different layers. The data always relates to the customer. We don't only provide applications to our customers, we also provide a development platform that our customer develops their own applications so they can enjoy the enhanced data that our solution provides and write whatever application they wish to their exact needs. And some things our customers can do, we cannot do, because they have the full fleet management application in the data center or in the automotive applications. They control the overall, and there is so much other types of data that are coming onto their systems. So now they can write their own applications on top of our, let's say, development kit that we provide.
What else can be done with this data? You've got a lot of data here. It's not just a matter of reading out this thing is going hot, or you've got too much power going through, or a signal's not coming through correctly. There are all sorts of possibilities that you can use this for.
Correct. At a very high level, it is used for some things we already mentioned, for example, for power reduction, performance increase, and lifetime extension, let's say 1 year of life. But also, it is being used very rigorously in tests, either in chip testing or system testing or in-field testing, and also correlating end-to-end. Again, the fact that today almost every entity is doing not just the chips, but also the systems and more, or vice versa. The end users are also doing systems and chips. So this whole thing requires that kind of data movement forward and backwards in order to ensure quality, ensure better reliability. One of the application is about reliability and failure prevention and predictive maintenance. That was maybe one of the first adoption of our customers to our technology. Since there is so much information coming out, and you can really differentiate things that are going well from things that are not going well, and predict failures, and so prevent failures, prevent silent data corruption, even in some cases where you can see that there is degradation in some of the internal paths. Things like that are also being used rigorously.
So when you get into these complex systems, multi-die type of implementations, you have a lot more elements that are going on here. Some things may behave differently over time in conjunction with other elements as well. So it's no longer just this device has failed and this one is working fine. It's now this device failed because it's next to this device. How do you go through figuring out who's responsible here?
First, I think I love the comment, because it's no longer a pass or fail story. It's very hard to determine pass versus fail today. In order to really know what's the issue, there is a need of a much higher, much more granular visibility into the parametric. But it's almost an analog view of what's going on inside. Otherwise, if you're only looking for pass fail, it's going to be impossible to understand where a problem is coming from. So the whole concept is to move from a pass-fail scenario to an evaluation of the health of each of a device and each component inside that device. That's a very important distinction. Rather than saying, you know what, this die fails, this die passes, no. This die overall health is 75%. This one is 100%. The other one is 96. The other one is 100. Therefore, the 75 is the most suspected. Why is that suspected? Click a button, you'll see where there are events that are not as healthy as they should be. So the whole idea, pass and fail is like population analytics. You see what's normal and you say, oh, this is abnormal. This is abnormal, so it must be not good. This is not sufficient anymore. Now, we need to know in each of the dies lying there how they performed compared to themselves. So suddenly, the need is not only to take, let's say, outlier behaviors from the sides of the Gaussian, but to be able to identify the marginal ones in the middle. And that's a very hard thing to do. Until now, there are very few technologies, if at all, that can tell you, you know what? This one looks normal, but it behaves differently than it should have been on a very personal level. The way to really tackle that is during the lifetime of a product, not just during test and saying pass fail, while the product is running, have a continuous way to evaluate its health and performance all the time. These are the more sophisticated applications that we're providing to the more sophisticated customers. So these ones are very helpful in multi-die scenarios because now you can see not a black and white picture, but a map of healthiness to pinpoint which of the elements is not the right one, and inside that element, which area or which thing is not operating appropriately, even if it's not failing completely. We call it, by the way, real-time health management.
And this basically is taking it in the context of the workload and the physical layout too, right? It's no longer just this is a chip and here's how it's working. It's now here's how it's working with this under these conditions in this particular workload that you're using.
Oh, absolutely. How could you guess? Let's say that you're the best company in the world doing tests and you do it testing for 50 years and you use all the techniques and use all the new statistics and the best manufacturing analytics. At the end, you ship a device. And the device is working in a completely different environment. And by the way, sometimes you don't know which workloads are going to come. So there is a huge investment in running benches and running different workloads. But even then, when reality comes, there are new workloads that have never been tested anyway. So you're right. There is no way to really guarantee today both the minimum power and the maximum performance and no failures, and yet to cover all options except to be dynamically operating all the time, every moment, every clock. There is no other way because you can never know. That's exactly the point. It's getting too complex. You have so many dies, so many stacks, so many things. You test it the best you can. You're the best, I'm not even doubting. 100% testing all the way, including system testing. Now it's working. There is this huge element with multi-die packaging and everything else, and it's working inside the data center under extreme conditions. Suddenly, there is a new workload that no one anticipated. The only way to deal with that is to be able to do dynamic configuration. And that dynamic configuration can do things without sacrificing too much power, without sacrificing too much performance, and without sacrificing quality or reliability. That's exactly the idea, and that's the purpose. Now, there are many ways to do that. And we're proposing one layer that is very granular and with an extremely high visibility so that it could really exploit the full guard band that exists without and guaranteeing no failures. That's the whole point.
Shai Cohen, as always, thanks for a great insights into what's going on in the industry.
Thank you very much, Ed. I really enjoyed our conversations, and I'm always taking a lot from your questions.